Now let's see the insertion algorithm for the heap data structure. Let's start with an example. We want to insert 7, 6, 9, and 4. Let's see it with the tree form. So first we add 4. Okay, nothing strange. Then we we need to add 7, not 4. Okay, there was something strange. 7. Okay. Then we need to add 6. Okay. So remember the constraints. We need to go from top to bottom and from left to right. So we are going like this. So we need to add an element here. We do add an element here. Okay, it's 6. But remember another constraint. The subtree, so I change color maybe, you understand better. Okay, the subtree, given a root, the root is 7, and given a subtree of that root, and the subtree contains only 6 in this case, every element of the subtree must be less than the root, but 6, every element in the subtree must be greater. The root must be less than every element of the subtree, but 7 is not less than 6. So we need to swap them. Okay. So we need to swap, and we do. We do swap them, and we added 6. Okay. Then what do? We have 7, we have 6, we have 7. When we add 9, and then nothing strange. 6 is less than 7, 6 is less than 9. Okay, and then we add 4. So 6, 7, 9, top, bottom, bottom right. Okay, so top, bottom, left, right. So left. This is the first space that is free. Okay, and here we have the same problem because 4, that is in the subtree of 7, is not less, 4 is greater than 7, 7 is not less than 4. Okay, so let's see in more detail how do we swap this time. This time we can see, of course, that is the subtree, but we are gonna draw a triangle. This triangle will have a name. No, it won't. It is another. Okay, but yeah, let's see this triangle. So 4. Now 4 is less than 7. Okay, but we need that elements in subtree must be. We need them to be greater than the root. But 4 is not greater than 7, so we need to swap them. So what do? When we add an element, we see if the parent element is greater. Okay, if the parent element is greater, that means we do need to swap them. So okay, forget about the triangle. That is another algorithm we will see later. So we just say is 4, or better, we need is 7 less than 4. If it is, then we don't need to swap. But if it is not, so this is not true, we need to swap them because the minimal element must go up, must go as the root of all the tree. So what do? We swap them, 7, 4. Okay, so now we have 6, 4, 9, 7, and it is not finished because this, I give you the insight that this actually is recursive. So now what do we do is check, okay, now I moved up, but now I am an element of another subtree. So now this is the subtree, and every element of the subtree must be greater than the root. But 4 is not greater than the root. So I say this only to explicitate that this is not a MinHeap. We need to swap again. So for the number 4, do say that until I don't reach the top, or my parent is less than me, I keep going to swap with my parent. So is 6 less than 4? No. So we do swap them, 6 and 4, and we obtain 4, 6, 9, 7. Okay, this is a MinHeap. This has nothing bad. So we finished, and we inserted 4. So let's write in the array for 4, 6. Remember top, bottom, left, right. So 6, 9, 7. Okay. And now we are gonna work with the algorithm on this array. So how it works, you already saw, but let's see the algorithm itself on the right. So we start and we say, yeah, if the heap is null, we create a heap and we insert as the first element the x element that is passed. Sorry. First, the function requires an heap, a heap that can be already built. For example, if I added already 7, 6, and 9, I will pass as a heap this and the new element 4, and this will be the input of the function. Okay, if heap is empty, if I receive something like this, then I will simply add return a heap with the element 7. Okay, so if this is a very stupid case, if this is not true, so the heap is not empty, what do I do? Well, first, yeah, let's add another bit of information. In the array, in orange, you can see that there is a limit of the array. Actually, I'm not telling you that we are using an infinite array, which doesn't exist, obviously. And there is a way to implement an array that resizes it itself without adding further costs. And it basically doubles its length every time it reaches maximum length. And if you do the calculation, it doesn't add to complexity. It needs, of course, to copy all elements in a new array that is double the size of the previous when we reach the maximum size. But if you do a calculation, that is not a problem. So we can consider that this is an infinite array. So if we have an infinite array, we do need a wall that says, okay, we have an infinite array, but our heap matters from the index 0 to the index wall. Okay. Everything that is right, the wall is bad numbers, something that we were not interested. There can be anything right of the wall index. So this wall is called heap size, the size of a heap. Okay, so you can see in the code in purple we have heap. Um, so when we are inserting a new element, okay, for example, here we have an array with, let's see, we added 1 and 2, and then we need to add 3. Okay, so the wall right there is here, because remember the wall points to the last element of the heap. So when we add an element after a wall, and then we move the wall simply, because we have an infinite vector, an infinite array, sorry. So what this code does is first adding the element, and second moving the wall. Okay, moving on with this, we have the orange code, in which we save. What do we do in this code? Oh, this code is the part, is the recursive part that I told you earlier. Is the part where we had 6, 7, and 4, okay? And from 4 we started to swap 7 and 4, and then to swap 6 and 4, okay? So if we add an element, so when we add an element, we save a j index to that element. So let's make the example in the array. So we add 6, 7, 6, 7, 9, and 4. Okay. Then we added 4, and then we move the wall with the purple code. Perfect. Now, what do is we save a j index in the element we added. Okay. Here it says heap size -1 because we moved the wall. So heap size is here and j is the previous. So we need to do heap size -1 because we increased the heap size with the purple code. And so we say sorry, I use orange to be coherent, while I'm not the root, okay, because the first element of the array is the root. So while I'm not the root, and my parent, and remember that this function, parent of j is an index, an integer, is equal to j divided by 2 floor. So it's constant the time to do this function. So if I am the jth index, I'm looking for the j divided by 2 floor if index. So if I'm not the root and my parent is greater than me, and remember your parent should be less than you, because every element in the subtree must be greater than the element in the root. So if my parent is greater than me, it shouldn't happen. I swap me with my parent. Okay, so there is something wrong. I need to fix it. So I swap me with my parent, and I update the index to my parent index. So what I'm doing here is, okay, we have 4, 3, 2, 1 indexes. Parent 4 divided by 2 is 2. So my parent is 7. for my parent 7 is greater than me, 4, 7 is greater than 4, yes, so we swap. So we have 4 and 7, and then we set j here. Then, what is the parent of an element with index 2? J is equal to 2. 2 divided by 2, 1. Okay, so this is the parent. And then we say 6 is less than 4? No, so we swap them. 4 and 6. And then we have j here. And here j equals 0. So we reach the condition. J is not greater than 0, so we exit the while loop. And we stop swapping. And then we simply return the heap. And what we return, in this case, we got as input 6, 7, 9, heap of 6, 7, 9, comma 4. In this heap, we wanted to add this element. This was the input of the algorithm, and as output, we got a heap with 4, 6, 9, 7.